We're now going to cover the command pattern. In addition to understanding how this pattern works in general, we'll also discuss how to recognize how the command pattern can be applied to perform user-requested operations extensively in the expression tree processing application. The purpose of using this pattern is to define objectified actions that enable users to perform operations on an expression tree processing app. Command provides us with a uniform means to process all user-requested operations in a common and extensible way. Let's talk about why we might need this pattern in the expression tree processing app. We'd like to find some way to be able to support the execution of user operations in verbose mode, where users are actually typing operations directly in either through a command line or entering them by clicking buttons in a graphical user interface. And we'd also like to be able to provide a way of supporting so-called macro operations in succinct mode. Succinct mode is much more just like a very simple calculator interface where you type an expression in and a result comes back to you. In both cases, we need to have some way of being able to let users enter operations into the system properly. So what are the problems? Well, we'd like to avoid scattering the implementations of these user-requested operations throughout the source code in a way that's brittle and hard to maintain. If the implementations are strewn all around the source, then trying to keep track of them, to evolve them, maintain them, other types of operations, document them, and so on, it's going to be much more difficult because they're all going to be strewn around in different places. Moreover, we also don't want to hard code the program to only know how to handle a fixed set of user operations, because that will impede our ability to evolve the program to support new requirements over time. So what we're going to do here as a solution is we're going to encapsulate user operations as command objects. This will involve several steps. First, we're going to create a hierarchy of user command objects that contain an operation method called execute to run the command, as well as state needed by the operation. The command itself can either implement the operation directly, or it can forward the operation implementation to some other objects. Let's take a look at the user command interface. This is going to define an interface for a command that will perform an operation on the expression tree when it's executed. We're actually going to define this as an interface using Java. We'll have two methods, one called execute and one called print valid commands. These methods will be defined by the implementation classes. The commonality here is we have a common interface for all the expression tree commands. They'll all have methods called execute. And the variability is that we can have different implementations of that interface, which can provide support for the different operations requested by the users. This turns out, of course, to be the Gang of Four pattern called command. The intent of this pattern is to encapsulate the request for a service or an action as an object. You should consider applying this pattern when you want to be able to parameterize objects with an action to perform, want to be able to specify, queue, and execute requests at different times, and may also want a way to be able to support multi-level undo and redo. Here's the way the Gang of Four book documents the structure and participants of this pattern, and we'll also map this onto the expression tree processing app as well. There's a base class called a command, which defines a method called execute. In our particular case, this will be the user command interface. There are then a variety of different subclasses or concrete commands that inherit or extend or implement the command interface or class. In our case, that would be eval command, format command, print command, macro command, and so on. And then we have something called a target, and that's going to be used to actually implement an action. In our particular case, this is going to be something called tree ops that we'll look at when we talk about the state pattern here shortly. And then there's some kind of invoker, something that's going to actually execute the appropriate command. In our case, this is going to be something called the input handler. And we'll talk more about input handler when we get to the template method pattern. Let's take a look at how we might actually implement the command pattern in Java for our expression tree processing app. There's a number of different ways we're going to do this. I'll show you one example here. We'll look at some other examples when we take a tour through the source code. The basic idea is we want to be able to encapsulate the execution of a sequence of commands as a single object. And we're going to use this in order to implement so-called succinct mode, where it's just a very simple calculator interface. So the way this works is we can go ahead and create a subclass of user command called macro command. And then the macro command will actually contain multiple user commands. And when the execute method is called on the macro command, it will iterate, using the iterator pattern of course, through all the various subcommands it holds in its internals as a vector in this case. and it'll call the execute method on each one of those sub-commands. In this particular case, it's going to end up calling the execute method on the format command using in-order format. It'll call execute on the expr command, passing in whatever the user typed in as the expression. And then it'll call the eval command's execute method to go ahead and take the resulting expression tree and evaluate it in post order and generate a result. Here's how we would actually implement this. The macro command implements the user commands interface. It has a vector of user commands called macro commands, and its execute method, as you can see when called, will iterate through each of the elements in macro commands, executing each of them in turn. We're now going to take a quick tour through the implementation of all this in our Java-based expression tree processing app, so you can get a closer look at how the command pattern could be realized in practice. The command pattern implementation is done in a number of different files in our expression tree processing app. Let's start by taking a look at the user command class. User command is an abstract class. It defines several abstract methods, execute and print valid commands. And it also defines a data member called treeops, which we will use to hold the expression tree that's actually the target of the commands. Let's take a look at a couple of different subclasses of user command. There's a number of them. They're all called something or other command.java. Why don't we start out by taking a look at format command. That's one of the most fundamental of them. As you can see here, format command extends user command. It keeps track of the requested format as a string. Its constructor assigns things appropriately. It passes in the treeops and so on and assigns that up to the parent's treeops data member. And its execute method simply calls the format method on treeops, passing in format. When we talk about the state pattern, you'll get a better idea of what treeops does, but just think about treeops as defining the object upon which you can invoke various operations on the expression tree itself. There's also something else I want to talk about just briefly here. You'll notice that we have a method called print valid commands. And print valid commands is used in verbose mode to instruct the end user what valid commands are legal at that particular point. And I'll just mention this real briefly here because it's kind of interesting. As you can see, what we're doing is we want to be able to print out these commands both for the command line version and for the Android GUI version. And rather than writing two different pieces of code, instead we use our strategy pattern implementation to grab the platform strategy that we talked about in the strategy pattern video, and then we invoke various operations on the platform strategy to output the menu of potentially valid commands to the user. And the implementation of this is very different depending on whether we're in Android or whether we're in command line. But we're able to abstract away all that diversity, all that variability by using the strategy pattern. So that's format command. You can see that all the commands basically work more or less the same way. Here's expr command. Expr command stores the desired expression like -5 times 3 plus 4. It's a user command. It works very much the same as before. It goes ahead and delegates to the treeops make tree method when its execute method is called. By the way, if you look at the command pattern discussion, you'll see that this is an example of a forwarding implementation of the command pattern. We actually don't do the actual behavior in the execute method. Instead, we go ahead and forward it to another object that actually does the work. I could walk through all the different commands that we have and show them all to you, but you'll see very quickly that they're all pretty much exactly the same thing. We will also see another interesting use of the command pattern implemented when we talk about the factory method pattern, which will be coming up in the next video. Now that we're done looking at the tour through the source code, let's go ahead and evaluate the consequences of applying this pattern. One of the benefits of this pattern is it helps to abstract the execution or executor of a service, which makes programs more modular and flexible. For example, we can bundle state and behavior together into an object. We can pass command objects as parameters to methods. We can extend the behavior via subclassing. We can delegate the behavior to other objects. So it gives us a lot of flexibility in how we organize our commands and how we consolidate them and centralize them rather than having them scattered all around. It also makes it possible to implement new commands easily by subclassing from some base class. Composition, which is what we showed when we talked about the implementation in Java, allows us to yield macro commands. So we can go ahead and make macro commands that subclass from command, and we can use these macro commands in any context that expects a normal command because its execute method simply delegates to all of the subcommands that it has stored internally. Another nice feature of using command, which we don't really use in the expression tree processing app, but is actually one of the primary reasons the command pattern is used in lots of other environments, such as graphical user interfaces, or various kinds of editing tools, graphic editing tools, text editing tools, and so on, is to be able to support arbitrary level undo and redo, where you basically have undo and redo stacks where you can unexecute previously executed commands, undo their state, and then potentially store them to be re-executed again later if you change your mind. If you've ever edited in various Microsoft products or in GNU Emacs or other kinds of things where you can undo and redo to your heart's content, you have a pretty good idea of what I'm talking about being able to do these operations forwards and backwards. One of the downsides of applying this pattern is you can end up with lots of trivial command subclasses. In our particular case, this wasn't really a problem because we only had a half dozen of them or so. But if you had a large application with dozens or hundreds of commands, that could start to get a bit unwieldy unless you understood the pattern. If you don't understand the pattern, you'll wonder why you're drowning in a sea of subclasses. If you do understand the pattern, then you'll at least have a good feeling for why all these subclasses exist. Another potential issue is if you end up supporting arbitrary level undo and redo operations, that may end up using quite a bit of memory. For that reason, some editing environments or some desktop productivity tools or other productivity tools only let you do a limited number of undos and redos. Maybe you get 1, maybe you get 10, and so on. But they don't let you do it arbitrarily. There's a number of interesting implementation considerations you should think about when you try to go ahead and apply this pattern. One of the issues is, should you copy the contents of a command and any state it may use before you put it on a history list? And the reason for this, of course, is if it doesn't have a bundle of all the state that it manipulated, then if you undo it and redo it, you may have a hard time keeping track of what's affected. If you do certain operations that do computations, you have to be careful about accumulating errors during the undo and redo. If you're using various kinds of floating point arithmetic, for example, and you undo and redo things, you have to make sure you're not subject to problems with rounding error. This is sometimes what's known as hysteresis. You have to be careful of that. If you're just storing data structures, then it's more of a memory issue than an error accumulation issue, but you still have to be aware of that. And you also have to decide what degree of effort you'll go to support transactional behavior for the commands. If you undo something and then you decide you want to redo it, but before you can finish redoing it, your program crashes, do you lose all that state? Has that state been stored in some transactionally persistent manner so that when your program comes back up again, it can recover the state where you left off? Do you store the undo state? And so on and so forth. Those are issues you have to think through carefully when you try to apply this pattern in practice. There's a number of different known uses of the pattern. Many different user interface environments implement command. There's implementations that are built into various tools that you've probably worked with. There's capabilities that are provided in Java with various undoable edit operations and accessible actions. In fact, another interesting example use of the command pattern is Java's runnable interface, which is most commonly used when you start threads, but can also be used for other purposes as well. For example, people who program with Android may be familiar with the concept of using runnables to post messages from background threads to the foreground user interface thread. It's also worth pointing out that there's a pattern from the Pattern-Oriented Software Architecture Volume 1 book, the so-called POSA 1 book, called Command Processor, which has a lot of things very much in common with the Gang of 4 command pattern. The main difference is that the command processor pattern tends to focus a bit more on queuing and on using the pattern for distributing computation between threads or between different processes that may be on the same machine or on different machines. So it gives a slight different twist to the Gang of 4 pattern, but it's still very much in the same design space. So to summarize the command pattern, we can use this pattern to ensure that users interact with the expression tree processing app in a consistent and extensible manner, and we can have a uniform means for processing all user-requested operations. We will very shortly talk about some other examples of other patterns that are different from command, but can be using the command pattern internally in order to simplify their implementation. And we'll do that when we talk about the factor method pattern next.